Welcome everyone to this of the SIAM Activity Group in Financial Maths and Engineering seminars. Today we've got two young researchers speaking. First up, we have Mesias Alfeus from Stellenbosch University speaking about modeling rollover risk, a general framework for modeling rollover risk. Mesias is a lecturer in Stellenbosch and previously did his PhD at the University of Technology, Sydney. Mesias, please, if you share your screen, looking forward to the talk. Thank you.
Yeah, thank you very much, Sam and SIAM Seminar Series organizer for the opportunity to present my work in this early career talk. I appreciate it, and I look forward to hear your comments regarding the kind of research I'm doing at the moment. So, like Sam said, I'm a lecturer at the University of Stellenbosch in South Africa. This is in one of the beautiful wine town called Martiland. And I'm going to talk to you today about a framework that we developed during my PhD, the one that I did at the University of Technology in Sydney. And this framework is for modeling rollover risk, which is a risk that justifies the existence of the higher or basis or market basis spread that you see in the market. But the rollover risk will become very clear to you as we go along. I'm in the Department of Statistics and Actuarial Science, and I'm in a discipline called Financial Risk Management. At the moment, we have some vacant position for a professor and a senior lecturer position in Financial Risk Management. I will share with Sam to distribute for those who are keen to apply and join this wonderful team. In my talk, I structure my talk in the following. I'm going to tell you a story of the basis swaps, and then we have to run an arbitrage strategy that one has to run in order to take advantage of the spreads that exist in the market. And then we'll look at the mathematical foundation, then we'll look at numerical result. But the main thing that I want to bring across is to make sure that we understand what is the main modeling idea and what are the extensions that we are doing at the moment. Interest rate market has gone through different stage of development that you have seen since the global financial crisis. Now we have seen LIBOR came to an end since the beginning of this year. And in particular, the funding liquidity and credit downgrade risk has led to a spread between discount curve for different payment frequency. And this is in contradictory to what the textbook theory says, that there is no spread that's existing, or the spread was too small to constitute an arbitrage profit. It has been almost over 10 years, actually, but there is no overwhelming consensus on how to model this spread that we observe in the market. So we are going to look at a model that actually try to explicitly model what justify the existence of this spread. And that's what it will come clear that the existence of this basis spread is because of the rollover risk. And then we're now trying to model this rollover risk in an explicitly stochastic model. Okay, well, let's just get started. What is a basis swap? A basis swap is when you exchange you do exchanging, but both legs are indexed on a floating rate. A normal interest rate swap, one leg is fixed and then the other one is floating, but a basis swap, they are all floating rate, but they are different. They differ on the payment frequency. Maybe one is a 3 months, then the other one is after every 6 months, for instance. So a tenor swap is when you are exchanging two floating rate payments. And then we assume in this case that they all based on the same currency, say US or maybe say Euro in this case. So usually a basis spread is added to a shorter tenor. So if you have a 3 to 6 basis swap, a spread is normally added to a shorter tenor, which is a 3 months in this case. According to classical textbook theory of no-arbitrage pricing, this spread was actually almost close to zero. Therefore, it was essentially neglected. But after the global financial crisis, this is no longer true. So it's no longer true because rate of different tenors that we have seen in the market, they follow distinct dynamics, indicating that there are higher level of credit or maybe higher level of risk that are existing in this rate. So recent studies, they say this is due to default risk. Some they said because of funding liquidity risk, or some will say it's because of both funding liquidity or default risk or credit risk. But in this case, we are going to postulate that this anomalies of basis spread that we see in the market is actually because of the rollover risk. Before the after the financial crisis, a rate of different tenors, they follow distinct dynamic. So we have now, after the global financial crisis, we have different tenors in the market. So you have 1 month with 3, we have 6 with 3, and also 3 with 12. Nowadays, you even have more tenors actually that are being priced in the market. So if you look at the LIBOR-OIS spread before the global financial crisis, it was pretty zero, close to zero, but now it rose during the global financial crisis, especially during Lehman Brothers bankruptcy, and then it came back, but it had been fluctuating. And you see also during COVID-19, the spread also just rose up and then came back, but still keep fluctuating. It's sort of like a stochastic. The spread between LIBOR-OIS is actually a measure of how the healthier of the financial institution or financial market. It's used as a barometer for the insolvency in the market actually. So if we look at what has been done in the literature, so we categorize the literature into 2 parts. There's a pragmatic approach and also fundamental approach. The pragmatic approach, these are the guys like derivative pricing guys. They just say they exist term structure for each tenors and there's a spread and that's it. And then they just come up with a model to model that for the multiple care framework. The fundamental approach guys, they're the guys who are now trying to model the exact risk that justify the existence of this basis spread. Like one of the paper by Maureen, Buchat, and Crepy, they talk about the existence of this basis spread is due to default risk. And there's more a paper by Filipovic and Troll in 2013 that came up with a model for an interbank risk. And then they divided the interbank risk into 2 parts. It's more of an econometric approach where they estimated the credit risk from the CDS, and then they just say the residual is funding liquidity risk. And then the key approach or the key reference in this case is a rollover risk approach that based on our paper jointly with Martino Grasselli and Eric Schugel in 2020 that modeled the rollover risk is a risk that a LIBOR panel member might not be able to roll over short borrowing because maybe this panel member will be faced with higher credit spread when rolling over short-term debt. or maybe the funding liquidity might just dry up. No one will lend, but you have to borrow in any case. So meaning your borrowing cost increase, and then that you cannot able to roll over your borrowing. That's what we call rollover risk. I'll keep repeating this so that at least you get an idea of what we mean by rollover risk, and it will become clear soon. So in how do you take advantage of this basis spread in the market? Suppose you have a 3 to 6, just an example of an arbitrage strategy that one has to run in order to take advantage of the basis spread in the market. So assume that the market is pricing, say, for a certain currency, the market is pricing, say, quoting 3 months plus 100 basis points against 6 month rate. Okay. So what you have to do, you enter a swap where you borrow at 3 months and then you rent at 6 months. So, and then you roll over for every 3 months. And then you enter a tenor swap. A basis swap, it costs you 0 to enter that. And then at every 3 months, then you get this amount, which means you have a 3 month rate, and then for its maturity. And so what you get, so your initial investment at time 0 is 0 because this will cancel. And so because you are rolling over here, this will cancel with what you're getting from the basis spread or basis swap market. And then what if you add what is the profit after every tenor, meaning after every 3 months, your profit will be 25 basis points. And then also in this case, because this at 6 months maturity now, this is at 6 months, this is where the maturity is. So you will get, so this is what you have to pay or what you get to receive, and then this is what you pay plus the notional, which is in this case is 1. And then if you add all this together, and you still get 25 basis points as your arbitrage profit. So that means in every 3 months, you sort of pocketing 25 basis points. So there's no interest rate risk here, but there is rollover risk that maybe your credit spread in this tenor within these 3 months might increase, and then you're unable to roll over your borrowing. You're unable to roll over this borrowing, and so that you're faced with rollover risk. And then another way is that maybe your borrowing costs might increase due to the absence of market liquidity risk, and that will make it difficult for you to roll over this borrowing to the next tenor. So that's why we call so you are faced with a rollover risk that you cannot able to roll over your borrowing. So now the same arbitrage example that you run, you can run it to take advantage of the Liois spread. So in this case now, we try to model explicitly the rollover risk that's made up of 2 components. One component is called the downgrade risk component, which is part of the credit risk. And then the other one is the funding liquidity risk, that your funding cost might increase and then you're unable to roll over. And so that's why we call the rollover risk is made up of 2 components. In here in our framework, so we denote RC to be continuously compounded short rate, or for the interbank overnight rate. And this is given by this equation, which means is some riskless rate plus the market aggregate credit spread. And Q here is just your losses given default, or maybe it's normally given as a constant, or you can actually just also calibrate it from the market. So most of the literature say RC is free of default because one no bank can default overnight. But in our model, we don't say that. We just say RC is a rate at which to discount fully collateralized derivative transaction as mentioned in the master agreement of the CSI or credit support annex of the ISDA. And so that's what we say. We don't say RC is free of default because the maturity is short and then no one can default within a night. Okay, well, then this is how you can compute the discount factor based on the overnight rate under a risk neutral measure Q. Then you define it here. Then the rollover risk now, we can model it by introducing pi. So this pi has two components. This is the tour funding liquidity risk, and then this is the credit risk for LIBOR, for each LIBOR panels in so this is what happened before. So you have a LIBOR constituent, which means mainly like in USA, 20 banks. And then each bank has a different credit quality, say lambda, this small lambda. The big lambda here is the market aggregate credit spread. So now the rollover risk is now the tour funding liquidity risk plus the credit spread multiplied by losses given default. So again, then how do you, if you now want to run the same arbitrage arguments that you have to run in order to take advantage of the basis spread. So now you borrow at shorter tenor and lend at longer tenor. That means you borrow at RC overnight, and then your payment will be this one. But this payment, you have to discount it at a rate which take into account the risk, meaning you have to discount at our risk-based rate plus the market aggregate credit spread plus the individual credit spread times Q. But if you simplify that, this will be RC plus lambda SQ. So now you discount this one by this rate, and then at the end you only end up, so the present value of this will be exactly this. If you discount this payment here with this rate, you end up with that. And then you borrow, so the argument is this: you borrow at shorter tenor, roll over, and then you lend at longer tenor. So like what you did, you borrow at 3 months, roll over your borrowing, and then you lend at longer tenor. So now in this case, you lend at the LIBOR, you lend at LIBOR and receive an amount 1 plus delta. So delta is just a difference between say day count conversion, and this is what you're getting. But for rollover, when you borrow at shorter tenor, definitely this is you discounted at RC, then this is your present value. But for borrow, so lending at longer tenor, so now this is your present value. But now we also need to discount this, but we need to discount this at a rate which take into account the credit spread. That means we have to discount it at this rate. And then we end up with this, the present value. Okay, well, because really what your initial investment is equal to 0. So that means this equation plus this equation plus this equation must all add up to 0. But we know that the value of OIS at inception is equal to 0. So that means you can compute OIS like this. And if you make the discount factors as subject to formulas, and then you end up with this. So with this equation, in this equation here, this must be equal to 0. I mean, must be equal to 1. That means this equation here cannot be equal to 1 because otherwise the funding liquidity risk is equal to 0. So, but we know that funding is equal to 0. So that means this equation here this discount, the one which is a little bit in red, cannot be equal to 1. And this is where we bring in the rollover risk in the model, or when we bring in the funding liquidity in the model. And so we can now make this equation, we can make LIBOR the subject of formula, because this one is equal to 1. And then we end up with our LIBOR that take into account of the funding liquidity risk and also the downgrade risk, which is given by. So we derive our LIBOR expression, and then next we're going now to assume a certain model. So we assume a d-dimensional Wishart process, which is motivated by the fact that we can able to take the covariance variance into consideration in the model. Then we can also be able to model the multi-dimensional risk in the model. Okay, well, where your RC, which is your overnight rate, is given by A, B, C, and O. This one are all some metrics, and X is a solution to this Wishart differential equation. And so the beauty with that is that you can express the Wishart in exponential affine model, and the moment generating function is given in this equation, which is very tractable, and then you can solve it either using Riccati ODE, and then we use here we're going to calibrate now to the data. So here you're pricing a swap with different tenors, and so this is like the model. This is the market on the right-hand side. Then we want to make sure that we fit our model to be between the bid and ask, and then we're using a global optimization, which is adapted simulated annealing to solve that optimization problem. We are currently using US data, but in the next extension is that we're trying not to use South African data to the model. And once we fit the models to data, so these are the parameters, the estimate of the model, and you see that all the standard errors are pretty close to zeros. And then we also see that here the estimate of the rollover risk over the period at the cross-sectional. So we also estimated the rollover risk there. And if you want to check the fit of the model, is that the model is always between the bid and ask. And the in-sample and out-sample performance is really good because these are in basis point. And also, if you look at a 2-year OIS bond, and then you look at how does it fit the model over time since 2004 to 2022, you see that the models fit well the data, and also a 10-year bond, so forth. And now if you want to go to fitting the models to multiple tenors, you see that for 3 tenors that you are fitting OIS, you are fitting 1 month tenor, 3-month tenor, 6-month tenor at once. The model also try to be between the bid and ask. And then this is the out of sample and in sample performance of the model. Like if you see, the error is pretty close. And then here we also fitting at 2 years to the basis spread. You see that our model also follow closely the market data. Then we can also, we went on further to estimate the model volatility. And the red one is the in-sample estimate. And then this is the estimated volatility, one component in the main diagonal of this metric. And then here, this one also is an estimate so we're able to estimate the implied model volatility from the basis spread. And the whole idea is that we now try to this model is consistent with the new market dynamic of you can use this model for pricing the new benchmark rate, which is the SOFR, and also instruments on maybe say options on SOFR, say new cap like interest rate derivatives like caps and floors. And this is also something that is ongoing. And the model, the important with the model is analytical tractable, and we're able to provide important features or important insight in a risk-neutral expectation about, say, rollover risk from liquidly traded data. We are trying now to adapt this also to South African data, not only to US data. I've seen that there are also some works that are adapting these models to Euro data, but the model has been proven to be trackable. The framework is that we contend that the basis spread in the market is because of the rollover risk, and this is the rollover risk is a risk that justifies why one cannot be able to take advantage of the basis swap in the market. And then another thing is that we can able to use the model to infer OIS from the South African market. And the OIS, for instance, rate is not is illiquid in South African market and also some of the emerging market. So we can use the rollover risk framework to be able to infer or to develop OIS term structure in the South African context. And there are some work in progress paper is available in this, and I think I should end here to let for the question. Thank you very much.
Thank you, Mesias. We don't have time for many questions. If anyone does have any, please do post them in the chat. I had one quick question. So these models are generally posed in the risk neutral measure, but a lot of default risk is not really hedgeable. So the market's very incomplete. So how well does this model fit in P measure? Because that's what I need usually for risk management purposes.
Yeah, that's a good question, but we never really try to compute this model in P measure. I think it would be crucial to do that for risk management purposes to see how one can compute it in P measure. I think that's a good comment, Sam.
Any other questions? Igor, please.
So I have a similar question, which is probably much longer to answer. So I'll postpone it to the end of the discussion, also related to what is this Q actually. But I mean, for interest of time, probably I'll skip this question now and ask it at the end. Okay, thank you.
Okay, well, thank you, Mesias.
Okay.
Let's move on to our second speaker, Yufei. If you're able to turn on your camera, share your screen.
Can you see my slides?
Yes.
Okay, then I will zoom it.
Well, we're starting on slide 2. Excellent. Okay, so our second speaker today is Yufei Zhang, who is a lecturer at the Department of Statistics at the London School of Economics. He recently finished his DPhil in Oxford under the supervision of Christoph Reisinger. He's going to speak about exploration and exploitation trade-offs in reinforcement learning and continuous time. So Yufei, please.
Thank you for the nice introduction, Sam. And hello, everyone. Thank you for being here for my talk. And first, I want to thank the organizing committee for the kind invitation. And I really appreciate this great opportunity to present my work here. So in this talk, I want to discuss continuous time model-based reinforcement learning. So in this problem, I'm going to consider controlled SD with unknown coefficient. And I want to find optimal control while simultaneously learning the dynamic. So such a problem appears naturally for most practical application for stochastic control problem because we always suffer from parameter uncertainty. So a key question here is that how do we balance learning the environment and also maximizing the target objective function? So which is often referred to as exploration and exploitation trade-off in the reinforcement learning community. So in this talk, I'm going to present a framework to systematically address this issue for linear convex models. So the talk is based on 2 joint papers with Xin and Anran from Berkeley, and also with Lucas and Tennant from Edinburgh and Alan Turing Institute. So more precisely, let theta be some fixed parameter, and we consider minimizing the cost functional J over all adaptive control process alpha, where for any given control process alpha, the corresponding state process X satisfy this controlled SD, where the drift involves the coefficient theta. And here F and G are given cost functions, which I assume to be convex in the state X and strongly convex in the control. So here I also omit some technical regularity assumption on F and G and to simplify the presentation. But in particular, I'm going to allow F to take value infinity and to be merely lower semi-continuous, which is particularly important for control problem with convex control constraints, and also for entropy regularized problem, because usually this Shannon's entropy is not that smooth. So one can show that if the theta is known to the controller, then the previous linear convex control problem admit a unique optimal control alpha, which is actually given in a feedback form, in the sense that this optimal control alpha can be represented as a deterministic function. Theta of the corresponding state process. And in practice, this feedback policy can be found by solving a PDE, which involves the parameter theta. So in the case theta is unknown to the controller, then we need to balance exploration and exploitation. So more precisely, we need to decide when we interact with a random environment in order to learn the unknown parameter, and then when do we take the optimal control based on the estimated parameter. So such a learning problem is often studied in the so-called episodic setting, which you can think about as independent trials. So more precisely, let theta m-1 be the estimated parameter before the mth trial, which I will refer to as an episode. Then, given this estimated parameter, the agent will going to exercise a policy, which may depend or which may not depend on this estimated parameter. And then she will observe a trajectory of the corresponding state process, which subject to this chosen policy. The expected cost for this trial will be given by the corresponding cost function of J. And then the agent can update her estimation for the parameter based on all previous observations. So then she can proceed to the next episode. So roughly speaking, a learning algorithm basically is this sequence of chosen policies. And then in a learning algorithm, we are going to exercise a sequence of suboptimal policies because we don't know the exact model parameter. So the performance of a learning algorithm is usually measured by its regret, which is defined by this quantity for each capital N, which is the number of trials. So the first term in here is actually the cost for the mth trial. And the second term here is the optimal cost you can achieve if you know the model parameter. So intuitively, this regret essentially quantifies the cumulative loss over all trials because due to this, this exercising of this sequence of suboptimal policy. So for example, if for all episodes you exercise the same policy, you don't change this episode you don't change this policy over episodes, then basically the term inside this summation will remain constant across all episodes. Then the regret essentially grows linearly in terms of number of trials. On the other hand, if these policies phi essentially become closer and closer to the optimal policy, then this term will decrease to 0 eventually, And then you expect your regret will grow sublinearly in terms of number of trials. So the goal of this learning problem is to construct an algorithm, which is a sequence of policies, such that the corresponding regret grows as slow as possible in terms of number of trials. Okay, so the most natural algorithm is actually the so-called greedy algorithm, in the sense that the controller always exercises the optimal policy based on the current estimated parameter. However, this simple example shows that actually this simple greedy policy in general can lead to a linear regret. So for example, let us consider some non-zero coefficient B1 and B2, and we consider this corresponding one-dimensional controlled SD, where it only involves the controlled process, and we have a corresponding quadratic cost. So then by the classical linear quadratic control theory, the optimal policy will be given in this affine form and this linear form, where this coefficient P is satisfied a corresponding Riccati equation. So now assume that this agent learns the system by only exercising the optimal policy based on the estimated parameter. And assume further that our initial guess for B2 is actually 0. Then by this formula, the agent will exercise a policy where the second component is actually 0. And then she can only learn about B1 after this exercise, after exercising this particular policy. Assume further that among all episodes, the estimation for B2 is 0. Okay. Then actually by this induction process, you can see that actually the optimal model and the optimal policy will never be learned. And actually this event holds with probability 1. Okay. So this simple example actually highlights the importance of exploration for this type of problem. So that's why in this work, we are going to assume there is this exploration policy, which has a finite cost, and also satisfy this linear independent condition. So intuitively speaking, this exploration policy guarantees that if you exercise this policy infinitely many times, then you can exactly recover the known model parameter based on the observation. Okay. So actually this exploration policy can be easily constructed if and only if the action set of this control problem linearly span the parameter space. So given this exploration policy, we are going to design a Bayesian estimate for the unknown parameter. So to this end, we are going to view the unknown parameter theta as a hidden random variable. And then given a particular policy phi, we want to estimate the parameter theta by observing the corresponding state process X. So here I emphasize that the agent only observed the state process X, but not the corresponding Brownian motion path. But because this we are able to choose this control policy phi, we also observe the corresponding control trajectory in the sense that this Z process is also observed. Then because this controlled SD, the drift depends linearly on the parameter theta, and it has additive Brownian motion noise. Then by the standard filtering theory, you can show that the likelihood of theta based on the observation X is actually given in this following form. Okay. So this actually motivates us to design a Bayesian estimate, in the sense that if we assume that we impose a prior distribution of theta as a Gaussian distribution, and then by the standard Bayesian formula, we can actually show that the posterior distribution of theta based on the observation is actually also a Gaussian. And the conditional mean and conditional variance can be updated correspondingly by the formula based on the observation. So then this observation actually lead us to this to a phase-based algorithm, in the sense that this algorithm will operate in cycles. For each cycle, the algorithm will be split in terms of exploration phase and exploitation phase. So more precisely, for the case cycle, we are going to first exercise the exploration policy, for one episode. And then we are going to update the estimated parameter based on all previous observations. And we are going to, then we exercise the associated greedy policy associated with this new parameter for MK episodes, where MK will be specified later. After that, we proceed to the K+1 cycles. So because of this explicit separation of the exploration and exploitation, the regret of this algorithm can be decomposed into in terms of two parts. So recall that by the definition of the regret up to the case and the nth episode is defined by this accumulated loss. And then because of the explicit separation of the exploration and the exploitation, it can be further decomposed into two terms. The first term is the accumulated loss because of this exploration. And the second term is the accumulated loss because of exploitation. In a sense, we are taking the greedy policies. Because that we assume that this exploration policy has finite cost, then you can easily see that the first term is actually grows linearly in terms of number of explorations up to the nth episode. So in the following, we are going to control the second term by the parameter estimation error. So in order to do that, we are going to make another assumption in the sense that this performance gap assumption. So more precisely, this performance gap assumption says that for any parameter theta 0 inside this parameter set capital theta, okay, and we assume this theta 0 is the true model parameter, then the corresponding performance gap between a greedy policy estimated based on an estimated parameter theta and the corresponding cost of the optimal policy can be controlled by the parameter difference. And then the module of continuity is determined by a constant R between 0 and 1. So a precise performance gap can actually be established based on the regularity of the cost functions. So for general lower semi-continuous cost, we can show that a linear performance gap in the sense that this R is equal to 1/2. And we can even show the optimal quadratic performance gap if the cost functions are sufficiently regular, such that like the linear quadratic reinforcement learning problem, or the cost function involves special structure, for example, like this entropy regularized control problem. So then armed with this performance gap assumption, let's go back to this regret analysis. Now we are ready to bound the second term of this exploration loss by the corresponding parameter estimation error, where the parameter, here, this theta m is the parameter used to design the greedy policy for the mth episode. So now it remains to balance the parameter estimation in terms of the number of exploration episodes. So here, this is the main result of this talk, in the sense that we are able to determine how to balance the explorations and exploitations. So in the general case, we are going to choose the number of exploration episodes for the case cycle as k to the power r, where r is the constant in terms of this performance gap. And then we can obtain this sublinear regret with high probability. So in terms of, recall that if this r is equal to 1, then essentially this result extends the well-known square root regret for linear bandit problem to a much more general setting. So here in this setting, we are only relying on the exploration episodes to improve the parameter estimation. However, in some case, we can actually show that these greedy policies from this exploitation episode also help to improve the parameter estimation, which we refer as the self-exploration property. So for certain this type of control problems, we are going to emphasize more on exploitation. In the sense, we are going to choose the number of exploitations as a 2 to the power k. And then we are going to obtain a logarithm regret if the corresponding quadratic performance gap hold, which in particular is the linear quadratic case. So in fact, it can be shown that for certain multi-dimensional linear quadratic learning problem, the self-exploration property is equivalent to a full rank condition of the corresponding control coefficient B. So now we are going to end this talk by examining the performance of this algorithm in terms of linear quadratic learning problem in the existing literature. So we are in particular, we are going to consider a 3-dimensional linear quadratic problem where where both A and B are unknown, and the cost function J is a given quadratic function. So we are going to sample the initial guess A0 and B0 from some standard from a standard normal distribution, and we are going to run the second version of the PEG algorithm with more emphasis on the exploitation. So in order to estimate the statistical performance of the algorithm, we are going to perform 100 independent runs of the algorithm, where for each run, the observation is simulated based on independent Brownian motion path. So the numerical result is given in the following figures. So from the left figure shows the relative parameter estimation error for each parameter estimate. Okay, so you can see that as the number of parameter estimates increases, or equivalent as number of episode increases, the estimated parameter actually converges to the true parameter. And we also observe that it is in practice it's much easier to estimate the the state coefficient A comparing to the control coefficient B. So similar things has also been observed for other adaptive control schemes. However, we also observe that a rough estimation for the control coefficient is already enough to construct a nearly optimal policies, which can actually be seen from this middle figure. So this middle figure shows that the relative error for the expected cost of the estimated policy compared to the optimal policy we can get for the if we know the model parameter. So you can see that actually eventually this that we almost design a quite good policy eventually. And for the last figure, it indicates this sublinear regret for this algorithm. So in short, so in this talk, I discussed 2 complementary aspects of model-based reinforcement learning. So first, we propose a framework to decompose a model-based reinforcement learning into a performance analysis of a greedy policy, and also the finite sample analysis for the parameter estimation. So the first part can be studied in terms of control theory, and while the second part can be studied by statistical learning theory. And based on this framework, we design a phase-based learning algorithm, and we prove that this algorithm can obtain optimal regret for a continuous time linear convex model. And the talk is based on the following 2 works, which can be found on arXiv. And thank you for your attention.
Thank you, Yufei. Questions? I suppose before we take questions, I just remind everyone that we're perfectly able to hang around and have a less formal chat. We'll turn off the recording in a few minutes. Before we do that, I'll start off with a question. Yufei, if you go back to your performance plots,
yeah,
I was just rather confused why the relative parameter error increases initially. It seems
why? Because that for the first 2 updates, it only updated with a very small number of episodes. So in a sense, it's more like basically this increase is that I feel that it's just because of Monte Carlo error. It's suddenly because this essentially I'm taking an inverse and based on a few trajectories. So then it's not, there's no guarantee that this one will increase or not. I guess the first few episodes is not.
It looks like it increases very consistently though. You've got very small spread around those points. It just seems a little odd.
Yeah, I don't know the exact reason why it increased, because I am expecting that sometimes it increase, sometimes it decrease. But yeah, but this is the numerical result. It always, okay, so at the zero episode, at the beginning of the zero cycle, they all start from the same estimation, right? So in the sense that this the variance at the beginning should be very small, I guess. But I don't know why it is it all increased at the beginning.
Mm-hmm. Other questions? Igor.
So can you show us one more time, at least to remind me, what is A and what is B? So one is in the dynamics and one is in the...
So if you look at this one, A is the coefficient before the state variable. Mm-hmm. So this is a linear dynamic. So yeah.
So
and B is
assume that I know B. Let's say B is 1. What is the method then doing? Is it something related to, or did you try to compare it to the classical adaptive control, where you literally on fly estimate your A through MLE or whatever there?
Yeah, I think that there exist papers which study this performance, this regret bound in terms of adaptive control, where they assume that one of A and B are known.
Yeah, exactly.
Okay, so then they can show that actually you can always get a logarithm regret. So for the linear quadratic case, because that this problem is relatively easy to you more or less you don't need too much exploration, I guess. But for this particular if both A and B are unknown, and people shows that okay, so there exists a paper which shows that for the adaptive control scheme, which you are consider an infinite time horizon, then the optimal regret you can get is in general is only square root in n for the linear quadratic setting. So yeah, then you maybe it's a common in a sense that then you see that I can get this logarithm regret for the both A and B are unknown. So this is particularly because that for this finite time horizon setting, you can show this self-exploration property in the linear quadratic case. But for the main reason is that for this finite time horizon control problem or finite horizon learning problem, the optimal policy can be time dependent.
Right. So no, that I understand.
Yeah. So that's why this time dependent structure helps to explore the space sometimes. Well, for this infinite time horizon, this is your optimal strategy is always a constant or a stationary policy, in a sense that it's difficult to have this self-exploration property.
Thank you.
So there's a hand raised. Is that you, Yufei, or is this another Yufei, Zhang?
I don't know whether this is my, I press something, I don't know.
I'll press allow to talk.
Hello?
Hello, another Yufei, Zhang. Please ask a question.
But I'm not Yufei. What?
Oh, it just says Yufei.
Why? That's strange.
It is.
If you shared your link, you might be logged in under someone else's name.
Oh yes, Yufei shared his link. That's why.
I see.
I saw. Hi Yufei, it's James.
I did.
Yeah, sorry. That explains. So I just had maybe a couple questions. One was just this self-exploration assumption.
Yes.
I perhaps missed it, but could you just comment on it? And the second thing was you do Bayesian estimation of the coefficients, and I perhaps I missed it, but I just wanted to understand how the variance of the estimates ties into the algorithm and whether you explore it. So maybe you've said it, it just was quite quick. So yeah.
Yeah, it's okay. So maybe I start by explaining the self-exploration property. Okay, so So for the first performance gap, which is essentially the optimal one is the square root. Essentially, I'm only relying on the exploration episode to improve the parameter estimation, because then essentially, even though I update the parameter based on using the exploration episodes information, in the analysis I don't consider anything any improvement based. I don't assume any improvement in parameter estimation based on by observing the exploration episode by observing the exploitation episodes. That's why it only gets a square root, because that I choose this MK in this way. Okay. For the self-exploration, it essentially says that in some case, the corresponding greedy policy also which supposed to exploit also help to explore. Okay. I will explain this in a mathematical way about when I answer about this Bayesian this variance of the Bayesian update. So in this case, that essentially I can show that because this essentially this exploitation episode also help to improve the parameter estimation error. So then I can emphasize more on this exploitation, which get a better regret bound. Okay. So this is what I hope this clarify this self-exploration thing. In the sense that means that the optimal policy already explore the space. Okay, so this is what I mean by self. So in terms of this Bayesian update, so actually, so even look like even you look at the scheme, it looks like the scheme only depends on this mean of the parameter estimation, which is theta hat, instead of the variance. So actually, the variance information is used to balance to choose this MK. Okay, so in the sense that this MK, essentially this variance will eventually tends to infinity, will collapse to this variance will essentially collapse to zero. Okay, and then we hope that this basically the parameter estimation accuracy is determined by how fast this variance collapses to zero. And then essentially, then we choose this MK. You see that here the regret is essentially in terms of is basically in terms of balance the parameter estimation and through the exploitation episodes, and we are able to bound this parameter estimation error in terms of the variance of this Bayesian update, and then we essentially choose this. We then tune this this number of exploration to make this order in an optimal way. So this is how the variance of this Bayesian update was used in the analysis.
In the tuning of the number of explorations.
In the tuning of the number of explorations, yes, exactly. More precisely, the tuning of the function MK.
And what is the MK again? Could you show?
So the MK is essentially the balance. So okay, so here we always, so for each cycle, we always exercise one exploration for simplicity. And the MK is actually a number of greedy exploitation episodes. So in the sense that this more MK means that the larger MK means that we are emphasizing more on exploitation. And then if a smaller MK means that we have more emphasize more on the exploitation.
Mm-hmm.
So is your exploration policy not dependent on the variance at all?
No, the exploration episode is just choosing something. Like in the bandit case, I'm essentially explore the dimension for each dimension. For you have n arms, then I explore one of them independently.
So there's no sense that you're able to use the variance to say this is the direction I really want to explore. And
yeah, we did not do that in this work, because that this essentially we want to make this regret analysis relatively simpler. So if you I think it's possible to couple it, and then we are somehow working on this in this direction. But then this exploration, the exploitation are nested together, and then which this analysis become trickier. But the Nash is very good at this. So
because if you think of like, you know, the bandit setting, then I mean, whether you're doing the frequentist and the upper confidence bounds or like the Bayesian bandits, it seems like you're always kind of using this variance, right? Sam, that's why I think I'm asking this. But here you're just using it to tune that parameter.
Yeah, but I feel that this somehow is also implicit. It's not directly used as this as the other bandit problem, but this also I think is also involved. It's more or less these policies or this learning algorithm is also a feedback function of the current variance, I would say.
Mm-hmm.
Jonathan, would you like to ask your question?
Hi, Yufei. Thanks for the talk. I've just got a quick question on the regret, the definition. I was just wondering, for a general problem, how do you evaluate the J when for the true parameter when you don't know it, or is it because in your numerical example, obviously it's a kind of toy problem, so you know what the true parameter in that sense to calculate the regret. I'm just thinking in general, for a general problem, how do you evaluate that?
Yeah, I think okay. So I think this regret is just a criteria for you to design a learning algorithm. Okay, so okay, so you see that actually in practice you don't need to evaluate this. What you need to know is that you need to know this performance gap. So this is more or less a regularity of the control problem.
Okay.
So you don't need to evaluate it. If you want to numerically demonstrate the regret, of course you need to know this model parameter, and you need to know how to evaluate this J. But if you want to if you want to design a learning algorithm, more or less you just need to know the property of this gap instead of this particular quantity of J.
Right, I see. Okay. Thank you.
No problem.